In this video, we're going to discuss feedbacks and flip-flops, specifically oscillators and RS flip-flops. Circuit illustrations coming from the book Code by Charles Petzl. Okay, we will be discussing in this video how one creates an oscillator. An oscillator normally is being used to create a beat for the computer to follow, like when transition from instruction to instruction. We'll also be discussing how a single bit RS flip-flop which can store the last output or remembers the last output. Okay, so here is circuit for an oscillator. You can see that from our the definition of our topic, which is feedbacks and flip-flops. The output is essentially going back to the input, which is called the feedback. Okay, so this is not gate. A NOT gate. So essentially, what happens is if the value of the input is 0, the value the output would be 1. So essentially, that will be 1, and then essentially the output will be 1. Well, since the current output would be being fed back to the input, this would becomes 1, and now the current output changes back to 0. Okay, so let's do another cycle where the output is returning back to the input. So it's being fed back to the input. So this becomes 0, and the input returns back to being 1. So since this is a NOT gate, the output becomes also another 1. So we can see here in the diagram below is that there's alternation between zeros and ones. So let's say we started in this value where the input is 0. So what happens is, since the input is 0, the output becomes 1 for a while, and then when the input is fed back, when the output is fed back, or when the one output is fed back to the input, the output is inverted, becomes 0 again. This happens for a while, and then another cycle, the cycle continues. Okay? Essentially, that's it. Okay, so let's return to the discussion with the RS flip-flop. So this is what we call the RS flip-flop. Okay, it's called an RS because we have two voltage inputs, which is for set and reset. Essentially, what happens is for set is if we close the circuit. If we close the circuit, then the inputs for the first. Okay, so let's notice first that we have two NOR gates. Okay, so again, okay, so NOR gates are essentially just OR gates with NOT and a NOT with a NOT, an OR gate with a NOT. So essentially, it inverts the output of 4. Inverts the output of 4. So let's continue with our analysis. We have value of 1 here. Yes. So the switch is closed. So we have a voltage of 1 here. And essentially this becomes 0 first. Okay. So what happens is since this is a NOR gate, so 0 or 1 becomes 1, and invert that, we have 0. Okay. Now for the second NOR gate, we have so that's for the first NOR gate. So what happens if the reset flip-flop is open? So we have the value of 0 here. So what happens is 0 plus 0 becomes a 1. So essentially, our light bulb is going to light up. This is a 1. Okay, so uh, okay, so since this is a feedback of 1, what happens is our the other input for our first NOR gate becomes 1 as well. So 1 plus 1, 1 or 1 is still equal to still 1, and invert that still becomes 0. Okay, so we have established that in our, let's say that S and R Q is equal to, if we have 1 and 0, the output becomes 1. Now, let's say that uh, let's say that we chose to open. We said that that such RS flip-flops can remember our last input. So let's prove that. Let's open this circuit. Let's open the switch for the set voltage source, and then let's see what the outcomes are. So let's remove this first. What remains is that we have an output of 1. So this we have an output of 1. So what happens is, since this becomes 0 and the output is and still we retain 1. 1 plus 1 or 0 is still 1. Invert that, and still have 0. 0 nor 0, or 0 or 0 becomes 0. Invert that, still to 1. So what happens is, uh, regardless if we close or open this voltage source or the set voltage source, we still retain the value of 1. All right. Okay, so returning back to the circuit, we see that essentially what happened is we have a 1 here, a 1 here, and a 1 here. So whatever we do with the set voltage, it's not being changed. The output's not being changed. Okay, so what happens if we close the reset voltage? So what happens is, so this becomes a 0. So it becomes 1 or 0. Okay, so let's focus in on the 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 NOR gate on the right. Okay, so this becomes a 1 and 0. So 1 or 0 becomes a 1. 1 or 0 becomes a 1, and invert that becomes a 0. So we have essentially changed the value of the the one the set value and changed it to 0. So essentially everything the 0 is being fed back to the to the first first NOR gate, and 0 becomes 1. 1 and 1 or 1 still becomes 1, and invert that still becomes 0. So what happens is, whatever since it remembers the okay, so we have initially we have reset the value back to 0. So what happens if we open the first switch, the second switch for the reset? What happens is we still have a value of an output of 1 or 0, so it becomes 1. It's invert that, becomes a 0, and we still have a value of 0 here for the output. So what happens is we retain the last value of 0, output value of 0, last output of 0. So all right. Okay, so we have this is still the same circuit, except that we want it to look symmetrical. So we have added not an inverse of Q here. So, but this is still the same RS flip flop. So what happens is, as we discussed earlier, uh, when we reset one to set S, we have set S to one, or set one, and we have the value of R for zero. We essentially store the value of one for our output, and when we revert our set value to zero, the circuit remembers the value for output, so returns the value of Q. Similarly, if we have uh, 0 and 1 for the inputs, where our reset value is 1, our output becomes 0. Now, if ever we switch back the or we open the reset voltage, we still get the same value of Q. So what essentially happens, we remember for if we it remembers the last value we have from the circuit. It remembers the last value from the circuit, and it retains that even if we open the circuit. Now, an S and R value of 1 and 1 is disallowed because uh, although it can be done, but it breaks the idea that Q the output of Q is the inverse of Q. The output of Q and the inverse of Q is not being true anymore. So this one is disallowed. Later on, we will see that uh, uh, this 1 and 1 SNR inputs is not necessary.